Cuman zip lah. Set zip.
Okay, okay. So we So we refresh back our last lecture. Ni really ada kan? The last lecture, okay, we talk about, we just want to refresh where all these tensor came from, comes from, whatever. Okay, this one. So we have these curvilinear coordinates, and each of these has dia punya plane, and this one have plane, and this one has their own plane, surface, not to call plane but surface. Okay, and this is O, and at this point it is very orthogonal to each other, orthogonal or perpendicular to each other. So we can define this thing as this is the axis, axis of or the parameter or the axis of the curvilinear coordinates. Axis u1, we call it parameter u1, u2, and u3. And we can define in two ways the basis vector of this. Basis vector of this we can define in two ways. We can define the first you already familiar with is the E1, E2, and E3, the basis vector. This basis vector, okay. E1, E2, and E3, where we can say that E1 is dr du1 over dr du1, or we can say that this is scale factor. We call it H1, okay. The E1 dr du1 1 over H1, we can say that. The other one, okay, E2 also just like that, is 1 over H2 dr du2, and E3 is 1 over H3 dr du3. Okay, we can say that. Okay, the other one is this. Oh, never mind. From here also. So this E1, E2, E3 is basis vector based on the unit tangent vector. They are also a unit tangent vector of the parameter axis of this axis. So unit tangent vector of this curve U1 is E1. Okay, unit tangent vector of this is E2. Unit tangent vector of this is E3. So they always unit tangent vector. That's why we can rewrite this in term of macam unit tangent vector. Unit tangent vector, the formula is dr du over dr du. So in this case, the basis vector is based on the unit tangent vector of the parameter, or the axis, parameter axis, u1, u2, u3. Okay. Well, the other one is The other one is, okay, at this point also part of this surface, kan? This is surface, or we call this surface is U1, U2 surface, U1, U3. This U3, this one U1, U3 surface, and this one is U1, U2 surface. Okay, and this is U3, U2 surface. This surface, surface of we define the surface of, because of there is a two axes here, U1, U2, U3. We have U1, U3 surface of this. So at this point, what if at this point there exists? It's not if. If there also exists, this point is perpendicular to each other for even for the basis vector. So another basis vector we can get is, we take this at this point at the origin. Let's say the vector that is perpendicular to U1, U2, okay, perpendicular to U2, U3. That's right, U2, U3, perpendicular to U2, U3. This surface, and so the vector is become like this. So we call it E1, capital letter E1. So U2, U3 surface perpendicular to this surface at this point of origin, we call it E1. Okay? Alright. Boleh? Faham? Okay. At this point, point of origin, perpendicular to U2, U3 surface is this E1. E1 basis vector E1. Dia perpendicular to a surface. Surface dia, surface U3, U2. 3 to E1. Okay? Now perpendicular to U2, U1 surface, this one. Perpendicular to this one. Okay. That is another surface. This is E1, U2, U1, E3 surface. So actually sekejap lah. Actually dia mesti perpendicular to each other. Dia perpendicular, dia nampak macam, I look at this, nampak just like tak perpendicular, but actually it's perpendicular to each other. This one, and then the other one is from U1, U3. So this is E2 surface. So this is, all of this is perpendicular to each other. So they have E1, E3, E2. So E2 perpendicular or normal to the surface U1, U3. This one, this U1 basis vector, this U3 basis vector, U1 exists, U3 exists, this surface. So this E2 is perpendicular to E1, E2, E3. Okay, E3, E2, E1. E1 is perpendicular to or normal to the surface. E3, E2. Okay, so far okay? Okay, and then another one, E3, perpendicular to U1, U2 surface. Okay, dia ada two ways to categorize, to derive or to say the basis vector. One is by we define the unit tangent vector of the parameter or the axis, which is this. You already familiar with it, right? E1, E2, E3. The other one is, if you have a surface, and this perpendicular to the surface. Where another surface, there is another perpendicular to that surface. Another surface which is at the same point, which is perpendicular to each other. There is another surface. Another basis vector. Another basis vector E, usually E, that is perpendicular to that surface. Okay.
E1 yang kecil. Bukan dia adakah dia perpendicular to U3 U2 juga?
Yes. E1, this one, E1.
Yeah.
This one perpendicular to each other, not necessarily perpendicular to the surface. Okay. So E1 is tangential, the small E1, tangential to U1. This is as usual, right? So there are two cases. Okay, this one. Okay. Bagi you all understood well. Okay, this one. U1, U2, U3. Okay. Okay. This at this point, perpendicular, tangential to U1, we call E1. I think you all are already familiar with this, right? And this U2 tangential to U2 is E2, small e. Tangential to E3 is small E3, is small E2. And those at the point here, the center at the center of the intersection point is everything is perpendicular. The U1, U2, U3, also the E1, E2, E3 is also always perpendicular to each other. It's perpendicular to each other. Orthogonal or perpendicular to each other. E2, E3, okay. E2, E1, E3, whatever. Okay, the other one is this. The other one is this. Okay. It has okay. U1, U2, okay. U3. And you imagine, okay, at this point, if you take it out, it's always perpendicular to each other. But as long as it goes, maybe they warp or they have some curve. Right? It's not necessarily straight line. It's curvilinear line. Okay. So so this one is U2 U3 surface. This is U2 U3 surface. This is U2 U3 surface. This one is U2. We label it U2 U3 surface. This is U3. It has U3 axis and U2 axis. And imagine at this point there is an axis perpendicular to this one. Perpendicular or normal to U2 U3 surface. So we define this as E1. Understand? Okay. And the other one is this. This one is we call it U1 U2 surface. U1 U2 surface. And exactly perpendicular to this U1 U2 surface, or normal to this one U2 surface, is U1 U2 E3. E3 perpendicular or normal to U1 U2 surface. Okay? Alright. And the other one, the last one is this. This look twisted a little bit twisted. Oh, say for example this. Okay, it's twisted. And this is, we call it U1 U3 surface. U1 U3 surface. This U1, this exists. U3, this exists. Surface of this Alright. At this point, perpendicular to U1, U3 surface is this surface. Okay, this surface perpendicular to this surface is E2. So E1, actually E1 and E2 also perpendicular. So we have E3, E1 and E2. And this one we have E1. Let's say I just a little bit disoriented here. So let's say it's called 3, this is 3, E1, 2, this is 2, so this is 3, this is 2, 1. It must follow the right hand rule. E1, E2, E3. All these are basis vector, which is like IJK, which is a unit tangent vector. For this one, it's a unit tangent vector. For this one, we call it unit normal vector. Also a unit vector, a basis vector, but also a unit vector. But it's not a tangential; it's normal to the respective surface. Okay. Okay, everybody. Okay. Now we understand this. So last time we have this E1, E2, E3 for this. Unit basis vector based on unit tangent vector. Basis vector based on tangential that is tangential to the axis. Okay. So we derive this last week. Let's say we have vector A, and then you have alpha 1 E1. Okay. So E1 plus alpha A1 A2 H2 dr du2 plus alpha 2 alpha 3 H3 dr du3. Okay, look at this. So we can say this H1A1 as a component of this, also a component of as a this is a component vector. Okay, but this is something to do with tensor. Okay, we take it as a contravariant. We put indices above. Okay, later we talk about contravariant covariant later. So A1 and this dr du1. Let's just put indices up. So we want to. So this one we can say indices up over here. No problem. We can down or low indices or low uppercase indices. It's okay for this. So you can put up this. So this one you take it as uppercase indices. Okay, A2 dr du2 plus A3 dr du3, and this is we call A. So we can always say this as a summation of dr du1 du mu, for example, mu. So mu from 1 to 3. Okay, from 1 to 3. So it's summation. Okay, dr mu. So this is a form of a tensor. Okay, a form of tensor. So we can rewrite this thing as we put some indices. Let's say this is indices nu. Okay, and so this is summation, and this is mu, and 3, and this dr dx mu a mu. So dr we can replace dr bar because it is describing this position vector here, describing the result is here. This is the result. So we can say that this is x mu. can rewrite this. So mu, mu. So mu, you expand this. So this is like what you call this is we call dummy index, and this is free index. Free index. This is free index. New is free index, and this is dummy index. It's called dummy. Dummy index. Or sometimes they call umbrella. So dummy index. Okay. So this, when we rewrite this again in terms of tensor. So this is tensor kind of tensor form of rewriting the whole vector. Ini vector, this vector, this is tensor. Tensor. So without without anything we indicate a summation, without this summation symbol, we call it the Einstein summation convention. So this is, it become like this. This bar dx mu a mu. So this is a form of tensor. What kind of tensor is this? This is, we call it a contravariant tensor. Why contravariant? Because you want to increase this, you have to you can increase this, but you must decrease this term, this denominator. So they always contra. The mu always contra. Okay, understand?
Bagaimana
dr become dx bar. Okay. This is just a normal representation of vector. Okay. But if you want to put in a tensor form, so okay, so this vector is as a result of this component vector multiply this with this vector. Okay, so that's why it is this vector this r bar, all this is in the same, what we call in the same region or in the same coordinate system of A. Same region, the same is the same. This is the same system, the same coordinate system. Same coordinate system. Okay, this representing a position vector, but we can always, we want to rewrite them in tensor. R is position vector. So we just take this thing as another form of a tensor, or another form of what we call of variables, but we put the bar here because it represent the transformation. It represent from here to here, which is this bar, the result of it, bar with bar, and this the agent of transformation, what we call it. Okay.
The mu is the number of
Yeah.
dimensions.
Not number of dimension, number of how many, okay, we can say number of dimension. 1, 2, 3, okay? The one for the vector. This one, 1, 2, 3.
But
Particular
what
dimension.
does the free index mu stand for?
Hmm?
Is that a mu and then there's dx bar nu?
Okay, this stand for what? Okay, good, very good question. This is what we call the free index. It represent one vector. This one vector. Let's say there is another vector. This vector, this vector 1. Okay. Let's say there is another vector. Circling or moving around this vector, right? So this vector is A2. This is another vector. So it's a form of another vector in another coordinate system, another system of vector tensor system. Okay.
So the dummy index represents the number of components.
Yeah. Dummy index represents number of components.
Free index represents number of vectors.
Yeah, number of vector around. So let's say for example we have forces. So this resultant vector force. This force resultant. They have this component. There's another force. This force 1. There's force 1. There's another force here. For example here. Okay, force 2. So this component has a component everything. So this force 2, this 4, this 1 and 2 representing by this new, by the free index. Okay? Faham? Understood everybody? Okay? Alright. Okay, now we start with here. Now, okay, you understand. So this is this from what we call, we define basis vector from unit tangent vector. We get this tensor of rank 1, we call tensor of rank 1, which is contravariant. Okay, contravariant. We call it contravariant. Why contravariant? Because if you want to increase the result of this, you have to increase this, but you have to decrease the other dia punya pair, the dummy index pair. You have to decrease. You have to increase one, the other one is decrease. So they like always contradict to each other, right? The pair is contradict each other. Mu and mu, this is the dummy index pair. One is increased, the other one is decreasing. Because you want to increase this. You want to decrease this. If you want to decrease this, we decrease this, and this thing we have to increase. So they always contradict to each other. Okay? Boleh? Everybody? Okay? Alright. Okay, now we try to do this. We expand this, okay? But this is defining the unit the basis vector based on the plane, based on the surface. Based on the surface. Based on the vector that is normal to the surface. Okay? I explained it just now, you all. Okay? Now we define this. Okay. Just to refresh. If you have surface, you want to find a normal vector here. We can always find this normal vector of a surface by, this is like surface phi, differentiate with surface with the del. We can always do this. This is a formula of the normal vector. So if we have this, so this is U1, U2, U3. The U1, U2 surface, this E1, U2, U3 surface is U1, U2 surface is E2. U3, U2 surface, this is E1. So, U2, U3 surface is E1. Okay. Okay. U1, U3 surface is E2. And then U2, U3 surface, it is U2, U3 surface, I mean this one. This one. Wah, dia sudah jadi U2, U3 surface is E1. Oh, already U1, U3 surface already there. So U2, there's one U1, U2 surface, UE3. Okay. So this perpendicular to each other. So we can say E1 is del, we represent this as U1, over del 2, E2 is represented E2. Because why we represent U1? Why you represent for E1? We represent E1? Because if we look in you focus zoom out, it is not actually, it is parallel to each other actually. This is U1 and this is E1. If you zoom in, it is not like diverse, but it is parallel. So we can always say that this actually is parallel to each other. This E1, this also this parallel to E3. The U2 is parallel to U2. Let's say, sorry. Okay, this U1, U2, U3. Actually, it is parallel to the is quite similar to this one also. Quite similar to this. Actually, it's parallel to because the axis of this, because the U1 is normal to U2, U3. U1 normal to U2, U3. So E1 is also normal to U2, U3, right? And this is what? E3. So E3 is normal to U1, U2. Right? So U3 is normal to U1, U2 at this point, at this. So and that's why the other one is E2. This is E1. Okay, this is E2. So E2 is normal to E3, E1 surface, and U2 is normal to E3, E1 surface at the point, at this origin. Wow. That's why we can say E1 is del U1 over modulus of del U1. Modulus of U2. E3 is modulus of U3. And del U1 is still a kind of a scale factor. So we can say that is 1 over H1 U1, 1 over H2 U2, 1 over H3 U3. Okay. Wow. Okay. Okay, now okay, everybody understand why we can say that this E1 is U1, because E1 and U1 is perpendicular or perpendicular, normal to the U2, U3 surface. That's why we can say that E2 and the axis U2 is normal to the U1 and U3 surface, and E3 or U3 is normal to U1, U2 surface. Okay. Okay. Alright. Okay, now kita start. Same thing. Same thing as above. A1. Now E1 plus A2 alpha 2. Now E2 plus alpha 3 E3. Okay, so now we put alpha 1 U1 over H1. Oh, we can put H1 with this one, so because this is a number, so H1 delta 1. So we can say U1 plus alpha 2 H2. Ini 2 plus alpha 3 H3 ini the 3. Okay. So we can say this is components. Component, because this is going to be covariant, so we put lower indices. Okay, so if A1, and this is you can just put for this one, for the basis, we can for the what we call the parameter, we can just put, because we want to make sure want to relate to this covariant, this must be contravariant if we want to covariant and contravariant. But okay, if we put here A2, we can just change. For parameter, we can just change indices. But for component, we define it as covariant, so lower indices. Okay, so you can also say this U1 A1, or the other side U2 A2, this side del U3 A3. Okay, and what is this? U1 A1 plus A2 plus this one is the side is the one U3. A3. Okay, and this we can symbolize this du1, du2, du1, ijk. This the what we call the del or the gradient of u1. And this x, y, z, and x, y, z is in the same region of A. In the same region of A. Okay, but this one u1, u2, u1 is in the same region, the same region or vectorial region or the same coordinate system with A1. Okay, just like this. Okay, this one. You see, A1 is the same region with U1. Okay, A1, A2 is the same region with U2. A3 is the same region with A3, U3. Similar to this, U1 and A1 is in the same region. Okay, U2 and A2 is the same region. U3 and A3 is same region. The resultant of this is regions of X, Y, Z. Region of X, Y, Z. Regions of X, Y, Z. If you look at that, R position vector is X plus Xi plus Yj plus Zj, right? So X, Y, Z is in the same region as A bar. So that's why we call it X bar nu, X mu. Okay, X mu and X A mu is in the same region. So now we can say this is this whole thing. Okay. I erase that one. Okay. It does it. Okay. So this A, the resultant, okay, we say, okay, I make a comparison. Okay, A is du1 dxi plus du2 dyj plus du1 lah, du1 also dz, and then a1, okay, plus j k, okay, j I, okay, and then du2 dx I plus du2 dyj plus du3 dz k, okay, and then this a2, and then the some more is du3 dx du3 dy du3 dz k a3, okay. Okay, this okay, this u1 and a1 is in the same region, so we can say that this is dx mu a mu, okay, summation, all of how we want to rewrite this in tensor form, and this x, y, z is in the same region as this, so this dx bar a bar, and maybe it has many other vector, so this is nu, so this is nu, so mu and mu here. So with Einstein's summation convention, Einstein's okay, mu is from 1 up to 3. Nu is for other, okay, nu maybe 1 to 2 only, kan? So it has 1 dx mu a mu for this 1, so it will come to 2, is the one is 2 dx mu dx 2 a mu okay. Okay, we can rewrite this. It has, maybe it has two vector, a1 and a2, and it has 3 components. Okay, mu from 1, 2, and 3, so become x mu dx. This is bar representing this region. So whatever we can write the whole tensor as, generally we can this the region of the bar region, mu a mu, okay, so mu nu, okay, mu mu. So this in the same region. This is the resultant region. This is the resultant vector. This in the same region. This is the other region. This one region. This different region. Just like yang atas tadi. This one. The U1 always the same region. The U or the parameters always the same region with the component. But the R, the position vector, is the resultant region, the same region with A bar, with the vector. Okay. Yeah. Yes. Oh. As I beritahu tadi, E besar dia based on basis vector based on normal to the surface. Okay, normal to the surface. So E1 normal to the surface, E2 dengan U2 dengan E3 this surface. Okay, it's normal to the surface. E3 is normal to the surface of U1, U2. Okay, yang di capital E lah. So E2 is normal to the surface of U1, U3. Nampak? Tapi E kecil dia based on tangential to dia punya axis. So E1 is tangential to U1. E3 is tangential to ni E2 lah. E2 is tangential to U2. E3 is tangential to U3. Ni macam unit tangent vector. So yang kecil tu dia based on tangential to the axis. Tapi E besar based on normal to the surface. Normal to the surface yang kalau okey dia ada U1, U2, U3. Katalah surface U2, U3, so this surface. Kan? Kita ambil yang simple lah. Okey. X, Y, Z. X, Y, Z. So this is ZY surface. Okay? Nampak? ZY surface. This is ZY surface. And this is XY surface. And this is XZ surface. Okay? And this is, kita boleh kata this is EY. EY is normal to the surface, normal to exact surface. Okay, normal to exact surface. And EX is normal to ZY surface. And EZ is normal to XY surface. Nampak? Sebab this one is dia tak ada curve apa, dia just a straight line coordinate kan. So unit tangent vector same thing. So E1, so this is E2, this is EX, EY, and this is E3. Yang kecil pun sama kan. Sebab dia not a curvilinear type of axis kan. Dia straight axis. Dia state apa ni, dia punya basis, dia punya what we call, dia punya axis dia straight line, x y z axis. Dia tak curve kan. Kalau dia curve dia ada tangent vector. Actually straight line pun ada tangent vector juga, tapi tangent vector dia parallel to the axis lah kan. Faham tak? And the surface is here. Kalau x y x, ni y z surface, ni surface. Ni sini x y surface, ni x y z kan. Ni x y surface. So the normal to the ni is E2, yang E besar tu. Normal to the surface E2. Same parallel to E3. E3 yang small tu sebab tangent vector. Sebab tangent vector is parallel to the axis of Z kan. Tangent vector 3 EZ. Tangent vector 3 sama parallel ataupun samalah dengan Z axis tu kan. Dia tangent, dia always parallel kan to axis. Tapi sebab Z axis also a normal to XY axis. Nampak? Faham tak? Okay. So beza, just beza the capital E, dia based on the parallel apa ni, normal to the surface, the correspond surface lah kan. Macam E3 normal to U1 U2, E3 is normal to U1 U3 U2 surface. U1 U2 surface is 1, so E3. Okay, so E1 is normal to U2 U3 surface. Okay, alright, this one surface normal. And then E2 normal to U1 U3 surface. Okay, everybody? Okay. Okay. Now we look at this. Okay. So far this one faham? Okay, faham. Okay. This one, U1 is in the same region as A1 ni, same region. Begitu juga yang atas ni. Kalau you all tengok sini U1 ataupun U1 ni dia same region dengan A1. Kan? Same region. Begitu juga sini U1 atas ni same region as A1. Tapi dia di atas. Kan? Tadi U1 di bawah. U1 di bawah, di denominator. That's why they contra. Okay. Now du1 is above apa ni nominator. And this one. Okay. So kita boleh rewrite this thing in term of tensorial form. This one. We already rewrite. Okay, we rewrite this thing in tensorial form. So this one in the same region of this. This one indicate this new ni indicate ada vector, some other different vector. Okay, this one vector maybe A1. Okay, this one vector, A2 another vector. Mu is how many dimension? Tan kata dimension. Dimension boleh kita kata dimension ataupun component dia, component of the vector. Okay. Kalau in 3D of course dia ada sampai 3 dimensional, 1, 2, 3. Okay, later kita talk about. So far okay? Okay, now kenapa kita kata, why we say that this is covariant tensor? So this is covariant tensor. Covariant tensor. This one is contravariant. Contravariant. This is contravariant, this is covariant. Why we call it covariant? Because think of the name. Mu, the same region, and nu, the other region. If we want to increase this, we have to increase this, and the dia punya pair which is in the same region also have to increase. So they if you want to decrease, and this one have decrease, and the dia punya pair also have to decrease. So they always to each other. That's why we call it covariant tensor. Okay? So faham? So you can see all the vector can be written in a form of tensor like this. Okay? Aku apa dah? Okay. Cepat. Which one I should? This one you understood already? This one? Okay. I erase that. Okay. So far everybody okay? Boleh faham? Okay. Okay, alright. Kalau tak faham, you can always come to my office. I can explain in detail even. No problem. You can anytime. If I in that office, you just knock me up, and then if I'm there, I will explain to you. Okay. So now we have two types of tensor. We can rewrite the tensor from the vector, right? Rewrite the tensor from vector, which is all these vector that I explained now. E1, A1 is contravariant. Okay, kita ambil this one. You need basis vector A1. Kita boleh tulis vector E2, tulis vector E3. Or never mind lah. Just write like a vector. Because I explained a lot over there. So this one E1, E2, A1, A2, E2 plus E3, E3. So this vector, we can write this thing as, this could be vector one, okay, this could be vector 2 and so forth, vector 3 and so forth. So this can be said as a new the new okay, bx mu a mu, okay. We can say this. This is a contravariant tensor of rank. They call it rank 1. Okay, later I talk about tensor of rank 1, which is equal to vector. Tensor of rank 1, tensor, contravariant tensor. Why we call it contravariant? Because this one. Okay. The other one is we have a, let's say A2 is A1 E1 plus A2 E2 E2 plus A3 E3, the capital letter. So it could be many other vector also. Maybe this one vector 1, this vector 2, this vector 3. The same lah, the same has the same component. Okay, so 1 and 2. All these things we can write in the form of tensor as this. Okay, maksudnya indices ni I put because want to show this covariant. This is patut kat bawah. So it's mu di kat bawah. Lower indices. Okay, sorry tadi lower indices. So lower indices. The x mu, okay, a mu. Mu, the one we write as upper indices and lower indices. So this contract each other. This is mu. This is different region. So this is covariant tensor of rank 1. Nampak? Got it? Okay. Covariant tensor of rank 1. So you can see this rank 1 tensor is a vector. Rank 1 tensor ni, yeah. Okay? Rank 1 tensor is a vector. Remember that. A vector is also a tensor, and vector is a rank 1 tensor. But tensor may be up to many rank, kan? 1, 2, 3 sampai kalau in generality we have rank 4 tensor, Riemann tensor rank 4. Right? So there can be many rank. So rank meaning it can handle many dimension. Can handle tensor is independent of coordinate system. You can write a tensor and without thinking of what coordinate system we are in. Only when we want to have the result, and then we put whatever coordinate system we want to calculate, right? But while operating the tensor, we don't need to think about coordinate system. Okay. All right. And maybe one of the example, I give you example of calculation. This one, okay? Mana? This one. This one, eh? This one. This one. This one, okay? All right. So example, I give you example calculation, and I want you try to another example exercise at home lah. When I say exercise, you do it. Maybe a tips to something. Okay, I think I write. Okay, very simple. The component of a you see the component of a covariant tensor tensor, okay, in the coordinate system, in the x coordinate system. I think before I proceed with this, in tensor we indicate things not very specific, not specifically like r or theta or phi for coordinate system, x, y, z. We indicate it as x1, x2, x3. Okay. Okay. Just what is this? Sorry. What is this? X mu. Right. For example, this x mu. X mu, and then we define mu. Usually we define as 1, 2, 3. What does this mean? X mu means x the other, it has x1, x2, and x3. Okay? X mu we have x1, x2, and x3. If we define this, if we define mu as x1, x2, x3, nu doesn't matter. Indices doesn't matter. Sometimes we symbolize this as A, B, any alphabet. So let's say, for example, we have x nu. We can say that nu, when we say that mu is 1, 2, 3, that means x nu means x1, x2, x3, same thing. But what is this? For Cartesian coordinate, okay. Cartesian coordinate, so kita ada x, y, and z. Okay, this is kita define as x1, this is x2, and this is x3. Okay, for spherical coordinate, we have r, theta, phi. So this we can relate as x1, x2, and x3. Okay, for apa lagi? Cylindrical coordinate, we have rho, phi, z. So that means this x1, this x2, this x3. So you see, in tensor, we doesn't care dia punya exist. We just symbolize it as something like x mu or x with indices, then mu it tells about the what is the indices represent for. For example, for Cartesian, x1, x2, x3. For spherical, because it could be many dimension, not just three-dimensional. Kan? Kalau if in string theory we have like 26 dimension, in M theory we have like 10 dimension. So we cannot define what is spherical or Cartesian, whatever. We can only define by using indices like macam ni. x1, x2, x3, x4, x5, x6. How many dimension it will be? Okay. Okay, understand? Okay, itu faham itu? Okay. Now kita go to example tadi. Erase, okay? Everybody? So everybody, we erase this. Okay, okay. Erase this. Okay. Okay. Now we take one example. So this is rank 1. This I'm talking about rank 1 tensor. This is rank 1 tensor. So I give another example for rank 2 tensor. What is rank 1, rank 2 tensor? Okay, I'll describe later. So this is one example for rank 1 tensor, solving in rank 1 tensor. The components of a contravariant contra talk about contravariant. Okay, the components of a contravariant vector or tensor. When I say vector, that means rank 1 tensor. You know already. The components, usually when we say components of a contravariant vector, that means this is a rank 1. Already, we know already, a rank 1, a tensor. When we say vector is a rank 1 tensor. In the x coordinate system, you call system, one system or one group or one coordinate system, another coordinate system, one region or region. I say just now I said region, so this all the system is okay. Are 6 and 3. Okay. The components of a contravariant vector in the x coordinate system are 6 and 3. The component is ada 1, 6, satu lagi 3 component of this in x coordinate system. Okay. Mana in x region, okay. Obtain its component in the x bar coordinate system. Obtain its components in the x bar coordinate system. Maknanya in the other region, in the disrupted region. In A bar lah tadi. This one. Given contravariant is one. Ni komponen ni A mu ni dia ada 2 saja. A1 dengan A2. Mana A1 and A2, A1 is 6, A2 is 3. That is in one region, in X coordinate region in X. This is X. Dia tak ada bar, X. Ni in one region, one whole region. A mu, A nu, one region, okay? This is X bar coordinate system. Dia komponen mana A mu dia ada A1, A2. A1 is 6, A2 is 3. Okay, nanti later kita, right? And obtain its component in the x bar coordinate system. Mana this x bar coordinate system? This x bar coordinate system. The other region. Okay. Tapi they given the clue, the X bar, if the X bar, they define how this X bar relate to X mu. How it must have a definition how X bar relate to X mu by this. So X bar 1 is equal to 7x1 square to the power 2. And the other one, X bar 2, 6x1 square plus 2x2 square. Okay? Yeah. So it must have between the two coordinate system, it must have relationship between X mu. This is relationship between X mu dengan X nu, X bar. X nu dengan X bar, the relationship. This X bar, X1, the 7x1. X bar 2 is 6x bar 1 square plus 2x bar 2 square. Okay, faham? Everybody? Yeah. You all okay? Okay. Okay. Okay, listen carefully It's very important. Okay, ini baru rank 1. Nanti I nak bagi you all do in rank 2. Okay. rank 2. Tak apa, try buat macam latihan. Tak faham, datang jumpa I. Okay, this is rank 1. Okay, rank 1. Okay. This contravariant tensor rank 1. Rank 2 later I begitu. Rank 2 macam mana. So, rank 1. Okay. Dia ada components of contravariant vector. Rank 1 in X coordinate system. So are 6 and 3. Maknanya okay, now kita tulis the equation dia this one lah. The equation contravariant tensor of rank 1. Rank 1 this one. The A nu, the X bar, this is one region, this is another region. Mu, ni mu region, this new region. Okay. Relate. So dia punya koordinat dia X bar new. Ni satu lagi koordinat dia region dia the other region is X mu. So the X bar coordinate system dia ada 6 and 3. Maknanya X bar coordinate system yang tak ada bar lah. X coordinate system yang tak ada bar, there's no bar, which is A1. This is component. Component dia ada 2. Jadi ada 6 and 3. So we can say A1 is 6, A2 is 3. Already kan? A1 is 6, A2 is 3. Okay. Now kita nak derive the equation lah. So we have satu new. Okay. So, okay. This is X bar okay, tak apa. So, kita ada 2 macam ni. Now, relationship between X mu dengan X bar new. Maksudnya X mu dengan X bar ni, how does it relate kan? By this equation, given this equation, x1 bar relate to 7x1 square. Okay. X bar 2 relate to 6x1 square plus 2x2 square. That's how the coordinate in region X dengan region X bar is related kan? This one. This equation, these two equation given. Okay. Now kita ada ni. Now kita nak apply this equation. Untuk apply this equation, okay? Okay, alright. Everybody? Okay. I apply this one. Okay, everybody? Yeah, padam. Okay. Okay, now kita from this kita write the equation of the contravariant rank 1 tensor. A new dx new A new. So now how many mu kita ada apa? Mu kita ada berapa? 2 only. But they have 6 component, 2 components. Satu you have 6 and the other one is 3. So ada 2 components only. Maknanya mu tu ada 2 komponen. Ada 2. Jadi the 1 and 2. So now kita boleh expand this thing. Kita boleh expand Kita boleh expand this thing by using summation assigned summation convention. This dummy index mu yang kat bawah denominator apa ni we call low indices, ini upper indices, dummy index. Okay, we can write this way. 1A1 summation dia A2. Okay, nampak? We can write this way. Faham kan? Asalkan dia summation. Asalkan summation. Tu berapa mu ada? Mu 1 up to 2 kan? So now dalam Einstein summation convention, Einstein yang buat convention ni. Sebab kalau dia tak buat this thing very impossible to solve different mathematics dalam general relativity. Very messy. So dia buat apa ni the mathematics of dia guna mathematics of tensor lah. So tapi dia buat cara summation convention ni untuk memudahkan lagi lah. Maksudnya you tak masuk pun summation ni, tapi you tahu by dummy index ni dia summate. Okay, dia summate between U1 A1 and this U1 dia ada, so 1 1 dengan 2 2, they add them together. Okay, so satu lagi dia, kalau you tengok situ dia ada x bar 1 dengan x bar 2. X bar 1, x bar 2. That means the new ada berapa? New ada berapa? New ada 1 and 2 also. Kan? Faham tak? The other region have 1 and 2 also. That's why. Okay, so kita boleh ada 2 equation sekarang. A bar 1 dx bar 1 new, maknanya new, bila new is 1, and then dx1 and then a1 plus dx bar 2 and then dx2 a2. Sorry. 1. Okay. 1 1 2 2. X bar 1, x bar 1 dia punya result dia 1. So satu lagi question dia is this. A bar 2 dx bar 2 dx1 a1 plus dx bar 2 dx2 a2. Nampak? Got it? Faham Okay? Dia ada 2 equation. Satu, this one. This is when nu is equal to 1. This is when nu is equal to 2. So mu dia ada 1, mu dia ada 1 and 2. Ni mu dia ada 1 and 2. Dia running dalam apa ni unit seperti 1 and 2. 2 2. Sorry. Okay, di 2. This is when nu is 2. 2 x bar 2 x bar 2. 1 1 2 2. Okay. 1 1 2 2. X bar 1 x bar 1. So we have 2 equation. Nampak? Everybody? Okay. Now we know already A1 is 6. 6 kan? A2 is 3. We define as 3. Okay. So this is 6, this is 3. Just we want to differentiate dx bar 1 dengan dx bar 1, dx bar 2 with dx bar dx2, dx bar 1 dx1, dx bar 2 with dx2, and dx bar 2 with dx1, dx bar 2 with dx2. Just we want to differentiate that by using those two equation given. X1 prime is to 7, x1 x bar 1 is to 7x1 square square. Dan satu lagi, x bar 2 is 6x bar 1 square plus 2x bar 2. We just want to differentiate that. We want to find this. Okay, kita differentiate. I erase this one. So we have two equations now. We have A1, x bar 1 is to 2x bar 1 over dx. With respect to differentiate x bar 1 with respect to dx1, multiply with 6. Okay, kita tulis macam ni lah. Kita tulis already. 6 di A1, 6 dx bar 1 over dx1 plus 3 dx bar 1 over dx2. Okay, ni satu. The other one is A2 is 6 dx bar 2 dx1 plus 3 dx bar 2 dx2. Okay, this one. So if you look at this, we have only dua benda yang kita nak cari. Dx bar differentiate between dx bar 1 dx1, dx bar 1 over dx2, and dx bar 2 over dx1, dx bar 2 over dx2. Empat differentiation kita nak cari.
Differentiate from that.
Yeah, we can differentiate from that one. Very easy. Okay. You all nampak? Everybody? Okay. So we have given that equation. So x bar 1. Satu lagi is equal to 7x. X bar 1 7x1 7x prime 2. 7x1 2. Satu lagi x bar 2. Cuba kita buat pelan-pelan. X bar 2 is 6x1 square plus 2x2 square. Okay, now we differentiate. Now kita nak cari this one. Kita dx bar 1 dx1. Mari kita tackle this one lah. Okay, dx bar 1 differentiate respect to dx1. So we have 14x1. Easy. So we have this already. So we want to tackle the other one, dx bar 1 over dx2. Anybody? Anybody? Everybody? Dx bar 1 over dx2. Dx bar 1 over dx2 apa? You look at this. X1 dia ada x1 saja. Dia tak ada apa ni x2. 0. Right. Very easy. So x bar 2 over dx1 kan? Kita ambil x bar 2 over dx1. Jadi kita dapat 12x1. Nampak? 12x1. Ini tak ada. No need. Okay? Okay. We have already. Last kali. dx2 over dx2 kan? Okay, so over dx2 we have what? 4x2. That's it. So we plug into this again. So we have like A1 is what? Is 6 dx d1. X1 is 6. 84. 84 x1 plus 3 dx1 dx2 tak ada, kosong. That's it. Okay, A2 x bar A bar 1 is x for x1, A bar 2 is 6 to x 1 apa dia? 12x1 kan? 72 x1. Okay, plug in 2x2 x1 12x kali 6 x1 x2 2x2 plus, okay, 2x2 over x2 jadi plus berapa kali apa? 3 4 12 kan? Very easy, right? Faham everybody? Senang saja. So I give you another example with rank 2. What is rank 2? First I nak cakap what is rank 2. No need matrix. Kalau besar, of course we need matrix. Kalau dalam tensor dalam relativity, we have 4x4 matrix. Okay, 3D space 3x3 matrix. Sebab apa in general relativity we have 4x4 matrix? Because we have time and space, kan? Okay. So now another example. What is rank 2? But what is rank 2? I padam this one? So rank 2 tensor, maknanya dia ada dua indices. Each of them ada dua indices. Each of the tensor ada dua indices. They have two indices each of them. Okay, rank 2. So rank 1 tengok dia ada only one indices. Rank 2 dia ada two indices. Okay, rank 2 in X bar region or X bar coordinate system, they have indices, two indices. Let's say alpha beta is equal to dx bar beta alpha dx bar beta, and then this xi katalah different, just simbol a, tak apalah, a dx b. Okay, this is how we write rank 2 tensor. This is a, this is b. So this in one region, a and b is one region. This is contravariant tensor rank 2. Rank 2 contravariant. Tengok, dia ada dua. Contravariant. Sebab apa dia kontra? Tengok AB dengan dia punya in the same region. AB and AB is in the same region. So if we increase A, we have to decrease XA. We have decrease B, we have to increase B, we have to decrease XB. Always contravariant rank 2. Rank 2, kenapa dia kata rank 2? Dia ada two indices. So rank 3, rank 4, rank 5. Rank 3 ada 3 indices, rank 4 ada 4 indices, rank 5 itu. Macam Riemann tensor, If you siapa yang join me general relativity, Tan always curiously join me Riemann tensor alpha, beta, lambda, gamma, whatever lah. Dia ada berapa? Riemann tensor is how many tensor? How many rank? Ada 4 rank. Dia ada, sebab dia ada 4 indices, 4 indices, 1, 2, 3, 4. Tapi dia ada contravariant, dia ada covariant. Ni dipanggil mix tensor. Mix tensor, 1 covariant, 1 contra, 3 covariant. Mix tensor dia ada ni macam Riemann mix tensor. Dia ada Riemann covariant tensor, alpha, beta, gamma, lambda, whatever. So Riemann this is covariant rank apa? How many rank? Rank 4. Okay. Covariant rank 4. You see? You will learn this thing in general relativity. This is Riemann tensor, what you call Riemann. There's another Einstein tensor. Einstein tensor nampak simple. Rank berapa? Dia berapa? Rank 2. Dia ada 2 indices saja. 2 indices saja. So Einstein tensor dia macam dia reduce the massiveness or the complexity of Riemann tensor into just rank 2 tensor, from huge complexity of Riemann tensor to only 2 rank 2 tensor. But never mind. So this is rank 2 tensor. So dia mesti ada 2 indices. Rank 2 contravariant. Okay, this one is just a synopsis. So I erase. So how to write rank 2 covariant tensor? Rank 2 covariant tensor is this. Covariant mesti kat bawah. Okay, and then X dia mesti A the same region as this. A dx B the same region as B. And dx A, dx alpha, dx okay. And this is AB. Tengok dia all lower indices. This is rank 2 covariant. Why covariant? Because we increase this, we increase A, we increase B. We can also we want to increase alpha beta. We have to increase A. We have to increase B here. We have to increase this here. So always increase. So always they working together. They increase, both of them increase. Sini decrease, sini kena increase. Also, or sini if you want to decrease this, sini decrease, sini bawah kena increase. They contra to each other. Okay, that's what we call contravariant is covariant. Okay, now so if you look at this, dia ada dummy index. Ada 2 dummy index. There are 2 dummy index, 2 umbral. One is A, the other one is B. Kan? Sini pun 2 umbral. A, B, B. That's why written always we have to rewrite them one upper indices, the other one is lower indices. As an dummy index. Dummy index always pair with opposing indices. Indices, upper indices and lower indices. Dia punya apa? Pair dia. So kalau contravariant ni pair dia. A, B, B. Lower indices okay, dia dekat lower index, dia dekat apa ni? Sini upper indices, tapi dia duduk kat bawah, dia kira consider lower indices. Okay. Faham tak? Okay. Like for example, this thing we can write this, okay? You want to rewrite this thing in tensor form. We say, let's say dx bar alpha dxa. We can write this form as a, let's say we write this form as b c, okay, b, this one b lah, b the a, okay, b alpha dengan a. So we can write this form. So that's why this is alpha is the upper index, a is the lower index. Okay. So and let's say dx bar b bar beta beta dxb. Okay. We can always write it as a b beta and this is b. Okay. So we can write this form. This whole thing is a alpha beta is equal to b upper index alpha, lower index a, b and then a b. Nampak? So alpha beta. The running number, the running number or the dummy index always a the upper indices pair dengan a the lower indices. B the upper indices pair dengan b with lower indices. So alpha beta yang atas ni. Ini we symbolize actually b ni is differentiation between dx bar alpha dxa. So we symbolize as b, satu upper index ni. This one represented upper index, this one representing lower index. This one representing upper index, representing lower index. So nanti you make question back, why you say why you tak upper index tapi you tak lower index tapi you tak xa kan? Tapi this one sebab dia denominator, it is actually the lower index. This one upper index, this one lower index. If we return this apa dx bar alpha dengan dxa, rewrite as b alpha dengan a kan? Alpha, this one is upper index, lower index. Nampak? Got it, everybody? Nampak? Okay. So this I just want to show you where is the index, where is the what we call the dummy index ataupun umbral tadi, kan? Dummy index. Okay. Okay. So let's say the contravariant tadi. Contravariant alpha beta, contravariant rank tensor dx alpha dxa dx beta dxb and then a alpha beta ab. Okay. So this is a b bb a b b is the dummy index. Let's say we have a alpha and beta. It's alpha beta running from 1 to 3. Okay, and then not alpha beta, a and b maknanya dia runs from 1 to 3. A and b is 1 to 3. So how and then alpha and beta they run from 1 to 2. So how we want to rewrite this in equation, in more, expand this in more elaborate equation. So alpha beta run from, so this is what we call, this is the free index. Free index, and this is the dummy index. AB. AB what dummy index? A B. So they always what we call ada pair. Satu kontra, satu the other one is covariant. Covariant kontra. Okay, dia ada pair dia. Always that is dummy index. We call it dummy index. So free index AB. Dia is not a it doesn't have a pair of contra and covariant. Tak ada, kan? Dia always contra, dia contra, in this case dia contra. Everything is contravariant. That's why you call contravariant rank 2 tensor. So the contravariant tensor maknanya dummy, dia punya free index dia contra. Always contra. Dia tak ada pair kontra dengan dummy, kontra dengan covariant. So that's why you call it contravariant. So A B. So how we want to expand this? Okay, so maknanya dia boleh jadi, katalah kita so dia ada boleh jadi komponen bar ni, dia boleh jadi berapa? Dia boleh jadi 1 1. So dia 1 2 3. Okay, tapi senang saja 1 2 boleh, 3 banyak sangat kan? 3 we have to define relationship between x bar dengan x. We have to define. Later we have to define. There is equation for this. Okay. So we have katalah 1 and 2. This alpha 1 2. So we have A11, we have A12, we have A21, and we have A22. So we have 1 2 3 4 possible combination. Usually 1 2 and A21 is usually symmetrical. Dia boleh same thing. A12 dengan A21 is the same thing usually. A22 dengan A11 is 1. So all there are four possible equations. 4 equations, not say possible, 4 equations. In fact, the A21 and A12 is always the same thing. Yeah. Maybe always the same thing. We can see later. Okay? And okay, how we want to write this? So we have 4 equations. So let's say 1 1, A11. So that means alpha and beta is 1. The x1, the x2. The x A, the xb. A, AB. So we have that. Nampak? A11, this is alpha, beta. This is alpha, this is beta, this is alpha, this is beta. Okay? So we expand. dx1a. Tapi A dulu. A can be 1 to 2. B also 1 to 2. So A pair dengan this A. So that means we can say dx1 dx bar 1 dxb and then A1b. Okay? plus, so A and B is 1 and 2, okay, plus dx bar 1 dx x bar 1 dxb A1, okay, A apa? AB, okay, sini. So ini now the running number 1 1 1 1 and then now is 2 2. Okay, nampak? Got it? Okay, 2 2. So now we have A11 dx1 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 with respect to dx1 dx1 bar with respect to dxb. Now B also a running dummy index. We can expand it B1 to 2. So we can expand like this. dx1 dx1 dx bar 1 dx1 A11 plus we concentrate on B. B here. dx1 dx 1 dx bar 1 dx 2 kan 2 ni after one first one 2 A 1 2. Now this equation, we expand this equation. Okay, this equation dx bar 1 dx1 dx bar 1 dxb. So we already, the first one we already expand the A. The A we expand 1 and the other one is 2. This A1 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 A2 A2 and then B. Now we, from this equation we expand B. So we expand B by B as the dummy index. So B, when B is 1 and B is equal to 2. Okay, everybody? Atas? Sana okay? Sana okay? Okay, now we have the other, this side. We can expand the same thing. So dx1 dx2 dx bar 1 dx1 b1 bs1 and then a21, okay, plus dx bar 1 dx bar 2 dx bar 1 dx bar x2 a22. So actually A21 dengan 1 2 dengan 2 you try. Maybe it's not necessarily not necessarily symmetry. We call it symmetry, not necessarily. But certain tensor like metric tensor, they call it symmetric tensor. Later kalau sempat we talk about metric tensor. So this one. So this is the equation. Kan? For A11. Kan? A12 the same thing. First you atas tu dx bar 1 dx bar 2 alpha beta 2 and then dx a dx2 and then this is a Okay, you try expand it. Okay, I give you example. Give you example. Try exercise. Go over.
Dah 12:56.
Oh, yeah. Itu I give you, I write an example, and you try to do yourself. Okay. Don't understand, you come to my office. But next week we have a midterm. Okay. So I give you